So this part A, where you define a variable, people usually struggle with that. Before I actually go over that, I am going to write the function, which isn't asked until later. But I think if I have the function in front of you, it'll help a little bit with defining a variable. So A, again, this was in the notes from yesterday, the 4-1 notes. A is always your initial value. B is telling you whether this is increasing or decreasing and by how much over time. So A is 150. They started counting in the year 2000. So our A value is going to be 150 since that's how many there were in 2000. B is not just 11%. Please don't just plug in the rate. B is either 1 plus or 1 minus the rate. Because this is increasing, this is exponential growth. When you have exponential growth, your B value is 1 plus the rate. If it was decay, it would be 1 minus. Now, our rate is 11%, but you never want to plug it in as a percentage. Move the decimal place, and it's 0.11. So B is 1 plus 0.11, or 1.11. So the function, we have A is 150, B is 1.11, and it's raised to the x power. So in A, it's telling you to define a variable. Well, it's your number 1, I think. We are going to define a variable for the function and state what it represents. Contrary to popular belief, I get this every year from a lot of students. A is not a variable. B is not a variable. Variable, think of the word varies, right? A variable is something that changes. A is never going to change. I was told that we start with 150, so A is always going to be 150. So that is not a variable. Same with B. It's going to be increasing by 11%. I can't change that, so B is always 1.11. The only variable that you have is X. So they're telling you to decide on a letter, basically, that you want to use. You don't have to use X. You can use whatever you want. But this question is asking for the variable and what it means in terms of the problem. So again, just because A is a letter doesn't mean that it's a variable. Okay, letters do not equal variable. A variable is something that changes. So depending on the year, X is going to change. That's why it's called a variable. So anyway, I kind of answered it. X is going to be the years. So more specifically, since we started in 2000, it's going to be the number of years that passed after 2000 or since 2000. So hopefully that makes more sense. Just because you see a letter doesn't mean you have to call it a variable. Okay, next, what is a reasonable domain? So does anyone want to guess a reasonable domain here? So part of that guess is correct. X is the years since 2000. So if it's 2001, let's say we want to know the population in 2001, it's only increased 1 year since you started. 2002 means it has increased 2 years since you started. So X isn't that big. If you were to use 2000 as an X value, you're you're telling me that we're measuring the population in the year 4000. So be careful. X is telling you how many times it's increased. And since it's per year, it's how many years that it has increased. So you can write it like this. We don't have an end to it because there's nothing specifically telling me when to stop counting. So we're going to say that it starts at 0 and goes to infinity. So either one of these is correct. I don't mind which one you use. I'm writing my explanation, but you don't have to write it. No, we are not going back in time. I don't know what happened in 1999. I can't use this function to figure it out. We're starting in 2000 and going from there. So part C I already did at the beginning. The last part, what will be the rabbit population. I want to give you guys a chance to try that if you haven't already. You are plugging in 25. If you were to plug in 2025, you're saying that it has been growing for 2025 years. But we don't want that. It's only been 25 years since 2000. So what you're going to do is the exponent first, 1.11 to the 25. Then you multiply. Make sure you write a whole number. Okay, so for the next one, a new Honda Civic costs $24,500 and loses 9% of its value the moment you drive it off the lot. That really happens. I don't know how accurate that percentage is. I don't know enough about cars to tell you that, but I can tell you that this does happen. The moment you buy a car, even if you get down the street and decide you don't want it, you've already purchased it, you've already had it on the road, it immediately loses value. So I need to make a note. Because of this, your A value is not 24,500. Once you actually own it, and once the car starts to depreciate, it is not worth 24,500. So once you lose that 9% and you have it in your possession, it says over the next 4 years, the Civic depreciates 10.5% each year. If you don't know what depreciate means, it means it's going down, it's decreasing. So this would be exponential decay. Then after the 4 years, the car is valued at approximately 58% of the original cost. So hopefully you're a little better with defining a variable now. Our variable is not A, our variable is not B. X is the only variable, it's the only thing that changes. X, since this is depreciating each year, it's going to represent each year after you have purchased the car. So next, what domain best fits this situation? Anyone have a guess of why I do not have the same domain as the last question? Yes. Okay, so someone said earlier that eventually the worth will get down into the negatives. And I actually have to tell you guys that it will not, because when I have this exponential function and I put it on a graph, it actually will never dip below the x-axis. There's a video in the Go Formative where I explain a new concept called an asymptote. Exponential functions have those. It's an imaginary line, but the graph never touches. So actually, if you were to graph this function that we're about to find, it will get really close to 0, and you'll think that it gets to the x-axis, and you will think that it hits 0, but it actually just keeps getting smaller and smaller and never actually touches 0. So I know that's a very weird concept. We'll talk more about asymptotes later, but for now, the value will never hit negatives because of the graph. So what was said in the classroom that you guys probably didn't hear is, in the question, it says that it's depreciating for the next 4 years. So the domain is going to start at 0 still, but we're going to stop at 4. What this means is, with this scenario, the car is only going to depreciate by 10.5% for 4 years. Once you get past that 4-year mark, I don't know enough about cars to tell you what happens, but it's either going to start decreasing quicker or decreasing slower. I truly don't know which one it is, sorry, but it's not going to be 10.5% anymore. That's why we have to stop the domain at 4. So if you wanted to know the price of the car after 6 years, we can't use this function. You can't plug in 6 because that won't be correct. We have to stop at 4 years. Yeah, so you'll see how quickly this depreciates. You'll see why cars can get marked down. All right, so you don't have to write the explanation, but I'm going to. All right, there's our explanation. So write a function to represent the situation. I told you guys in the very beginning that A is not 24.5. The moment you drove it off the lot, it lost value. So we have to figure out what it's now worth before it starts to depreciate. So it lost 9% from 24,500. There are a few ways that you can do this. We lost 9% of the value right away. If you lost 9%, that means you're left with 91%. Again, there are different ways you can do this. This is just one of them. If you get the same answer that I do, great. You can do it that way. So in math, the word of means multiply. So if you want to know 91% of 24,500, when you have the word of in a statement like this, you're going to multiply 91% as a decimal times 24.5. So when you do this multiplication, that would be the actual value of the car once it's in your possession. And that means it's now worth $22,295 before it even starts to depreciate. So that's the actual A value. We also need B. We said that this is going to depreciate, so that means B is 1 minus the rate. When it goes up, when it's increasing, it's plus. This is decreasing, so it's minus. 10.5% is 0.105. Subtracting, you get 0.895. So that's your B value. So there's our function. The last thing we're going to do is use this function that I just circled to prove that after 4 years, the car is valued at approximately 58% of its original cost. So what I'm going to do is figure out, according to the function, how much this is worth after 4 years. So go ahead and do that first. I'll give you a second to figure that out. Make sure you use your order of operations. You would do 0.895 to the 4th power before multiplying by 22,295. You should get over 14 grand. So make sure you can get that on your own. You do need to know how to use the calculator to get that. So after 4 years, we just found that. We want to know if this is 58% of the original cost. The original cost, remember, was $24,500. It's how much you initially paid for this thing. So we want to know if it's 58% of what you paid. Remember, you paid $24,500. So we're going to divide the number we just got by $24,500. When you put it in your calculator, you get a decimal. That decimal is approximately 0.58. If you turn that into a percent, it is 58%. So we can verify that the function does tell us 58% of the original cost after 4 years.